Everybody. I'm happy that you are here today, and we are going to talk about a new initiative, new Israeli initiative that is now forming, and this is the establishment of Regional Climate Computation Center, and we'll get into this in these presentations. What we have here in our panel, we have with us the Chief Scientist of Ministry of Environmental Protection, Professor Noga Kronfeld-Shor. We have with us the Chief Scientist of the Ministry of Energy, Dr. Gideon Friedman. We have with us today Professor Colin Price of the Tel Aviv University, the head of Climate Initiative, right? And we have with us Dr. Kleanthis Nikolais, the director of the Cyprus Department of Meteorology. And we will try to explain why do we need a climate computation center, what it is good for, and what kind of outputs this center will give, not only for Israel, but for the entire region. And this was, of course, the rationale for the international collaboration that we have in this center. So we will start with the users. We'll start with the chief scientists of the Ministry of Environmental Protection and of the Ministry of Energy, which will explain why they need high-resolution climate modeling outputs for the adaptation plans. Then we will move to Professor Colin Price, who will explain the science and why there is a difference when you go to high resolutions. Then will be my presentation. My name is Nir, by the way, Nir Stav, the head of the Meteorological Service, and I'll explain how it's going to work. And then we'll have Dr. Kleanthis from the Cyprus Department of Meteorology that will explain why this is an initiative that is important for the entire region and why Cyprus and Israel decided to partner in the production of high-resolution climate modeling. So, Noga, the floor is yours.
Thank you, Neil. So you can move to the next slide. I'd like to start by describing three facts that make Israel interesting and complicated in adapting to climate change. And the first is that Israel is located in a meeting point of 3 continents and 4 geographical regions. We have a steep altitude gradient from more than 2,000 meters high mountains in the north, the Hermon mountain, which snows during the winter. And in the south, we have the Dead Sea, which is the lowest part on Earth, minus more than 400 meters. We also have a steep rainfall gradient from more than 1,000 millimeters a year in the north to less than 50 millimeters a year in the desert area in the south. We have a long shoreline, and the Syrian-African Rift Valley is crossing Israel. So all this makes Israel very diverse in terms of the land itself. We're also a very small and densely populated country with a rapid population growth. So the population currently is around 9.4 million, and it's expected to grow to around 20 million in 2050. Our annual population growth rate is about 2% per year, which is very high compared to other developed countries. The land area is about 22,000 kilometers, and 93% of the population lives in cities. So based on these data, we can see that Israel is one of the most densely populated countries in the world. And as I said, the population is still growing, and that this high density results in high demands for land, for water, and for importing food, for example, which results in increasing number of alien species. And as you can see in the figure, the trend is that Israel is going to be the most densely populated country. Next slide, please. It is also located in a climate change hotspot. You can see on the right a figure from the sixth report of the IPCC, the Working Group 2, which maps water scarcity in the Middle East. And you can see that our region is expected to experience high water scarcity compared to other regions in the world. And we also see from the Israel Meteorological Service that the trends in the increase, the average summer temperature, the increase is also high compared to the world average. So next slide, please. So Israel has a high need to adapt to climate change on top of acting to mitigate climate change. And we have several predictions to the situation in the future. For example, we can see that Israel is expected to be warmer than in the future. And can you press the next? I can do this, sorry. I'm tired. And we have to take action. So you can see that there's a governmental resolution 1022 for shading and foresting cities in order to reduce urban heat islands. We just issued a call for adaptation plans and pilots in over 20 local authorities. We're expecting sea level to rise and preparing to it. There's a government resolution 4079 with a commitment to complete adaptation plans in all ministries by 2023. We expect it to be drier, and another government resolution decided on the establishment of a Desert Tech Center, which focuses on climate change in dry climates as part of a new innovation zone for desert technologies in Beersheba, and the establishment of a National Committee for Sustainable Systems, Sustainable Food System, and Food Security. We are also expecting the weather to be more extreme, and to deal with that we have several resolutions. A new reference scenario was just published for flooding, fires, and extreme heat waves by the National Emergency Management Authority, and a new surface runoff regulation was published by the Israel Planning Administration. There's Government Resolution 1091, a national plan to deal with forest, woodlands, and open space fires, and Government Resolution 207 for promoting infrastructure and managing flood risks. But all these demand information. To implement all these decisions, we must have high resolution information to make actions more efficient. So two large decisions are looking at the information sources. One is the establishment of National Climate Computing Center by the Israeli Meteorological Service, which is the subject of our meeting today. And the other is the establishment of a climate adaptation portal by the Ministry of Environmental Protection, which I lead. So we're going to hear about the National Climate Computing Center today in more details by the next speakers. And I just want to say a few words about the National Adaptation Portal. And if you are here tomorrow at 10, we have a whole meeting focusing on this on this climate adaptation portal, and the idea is to optimize decision making across all sectors, from the government to local authorities and to the private sector. We need high resolution information, spatial resolution, about the risks, the vulnerability, and the adaptive capacity to climate risks. And what we are trying to do now is to produce high resolution street-level models for floods, urban heat islands, and wildfires. At the moment, we are doing it with a modeling approach based on international model, which we would like to replace in the future with the results of the National Computational Center, which will be much more accurate and validated. And what we are currently working on is producing vulnerability indices and maps. You can see here, for example, in the center that we can choose, for example, urban heat islands and as a sensitivity health. And you can see at the bottom at the map, you can see in one of the towns in the center of Israel, these are urban heat islands, and the green dots are a daycare for children under the age of 3, which have high sensitivity to heat islands or to heat load. And you can already see that without predictions today, there is a daycare facility that is located in the middle of a urban heat island, which means that we have to go to this specific daycare facility and make sure that we reduce the heat load, for example, by shading or by air conditioning. And eventually, we don't want to just show the risks and sensitivities, but also to drive the users into actions. So the portal will also include a response toolkit, which will include information sources, governmental decisions, funding sources, etc., in order to help the local authorities, for example, to mitigate and act in order to increase resilience. So to make this portal more accurate and validated, what we would like to get from the new computational center is information, for example, on sea level rise and coastal flooding, on fluvial and pluvial flooding, on fire risk, drought risk, urban heat island, and more. And as soon as we will start getting these data and information, we will update our portal, and I hope it will be used by as many as stakeholders as possible. So we are waiting for you to act. Thank you.
Thank you, Noga. And now the perspective of the Ministry of Energy and the adaptation needed and what kind of information is needed for the adaptation. Please, Gideon.
Thank you, Nir. I'm happy to be here to discuss a little bit the effects of climate change on the energy market, explain a little bit about this, and also what we would like to see from the capabilities of a computation center. Again, I want to start with the numbers. The way we look at it, there's going to be major changes in Israel within these 30 years. We use the prediction for the population I see slightly different than what Noga is bringing, which also brings us to a point in Israel which is very important, that the information will be the same, that everybody is using the same information. Hopefully, at least for the climate, we will have one platform, which will be an advantage. If we have a good platform, then we can all use the same database and the same information. So basically, our calculation uses, I think, 1.8% annually, and we get 60% increase in population. In terms of water consumption, we expect from about 2,400 million cubic meters to 3,500, about a 45% increase in water use. In terms of electricity consumption, we see a huge jump because actually the electrification of all the energy market makes this a big jump in the amount of electricity from about 70 today to about 160 terawatt hours annually. So these are very big jumps. In terms of climate change, if we talk about a few centigrades increase in temperature, we do not expect the climate change to affect directly the energy market more than, I estimated something like 15%. So I call it a second order, let's say, effect, but I will show a little bit later that not only the big numbers play, but also the variability. So in terms of the energy market, we face tremendous challenges. We have, if we want to go solar, we have a land shortage. We need to allocate perhaps up to 1 million dunams to do solar. We need to at least triple our electricity grid. We need to provide energy storage, electricity storage from 0.3 gigawatts today to 40, so this is a 100-fold increase. And for that we need technology, by the way. Yes, we will not be able to do it with the current technology. I think to do it easily we would need a 10 times improvement in the technology here. And we do want to do the carbon capture. So all of these are tremendous challenges that we face. And in this sense, we do not feel that climate change is very important because the challenge is so big. So a few percent here and there are not going to change very much. This is was provided to me by Neil, the meteorological survey. So we discussed a little bit the water. We see a predicted decrease in water supply. It's not negligible. Let's say it's of the order of 10% decrease. But again, in the game of big numbers, it's not a game changer. But every percent actually counts. If we want to put a new desalination plant, then even a few percentages will affect. We don't need to make the decisions today, of course, for the extra plant. So how does water affect us in the energy and water? Of course, we need to provide, when it becomes hotter, we need to provide more water. When we have less precipitation, we need to provide water to the land and to nature as well. So we see that as part of our responsibility. This was a shift at the ministry. We want to be able to keep the natural habitats as well. So we are thinking about water not only for our use, but for nature. I think the key line is the third line. Because, as I mentioned, the climate change is second order in this, but if we have, due to a few percentage change in biodiversity, this may have significant effects on what is happening. For example, if we are talking about the ocean, we are using the ocean to provide the desalinated water to Israel. And if all of a sudden, because of a 1 degree change, the population of the algae changes and we get toxic algae near our sources of the water, this changes everything. So we really need to understand better, and there is a big risk in changes in biodiversity. This is something we need to take into account. In terms of electricity, higher temperatures, of course, require us to put in more air conditioning, use the air conditioning longer time over the year. It will affect the peak demand, which is the highest demand during the day, which is what determines our capacity requirement, so how many power plants we need to put. So the peak demand affects it, and the temperature, we predict that higher temperatures will affect the peak demand. There is an effect on the power generation from turbines. So if we use today gas turbines, but even in the future, if we use green hydrogen and in turbines, then the generation during hot days is lower because the temperature, we need the temperature difference. And it's not zero, it's not very, very small, but it's of the order of 5 to 10% lower generation in the summer. Of course, if we rely on renewables, PV and wind, then the climate has an effect. Higher temperatures, then we get a little bit less PV production. What will be the wind patterns? If we will rely somewhat on wind for generating electricity, then what is going to happen with the wind patterns, and how are we going to rely? Again, I mentioned the biodiversity here for the desalination and this effect as an example, but it's difficult to predict what effects the biodiversity changes will have. And I now come to the main point, the way I see the need for a climate computation center. I think it is very difficult to predict, to run the models, and the details of the models are really unbelievable in the number of parameters and the number of assumptions that are taken in order to run a model 30 years ahead of time. So it's a big challenge, and I think just tackling the challenge is very important in terms of the knowledge that we gain, thinking about all the parameters that are affecting and how the models run, which has, I think, a very important scientific value. But eventually, as Noga also mentioned, what may be more important is the variability, the variance of the climate. So maybe it will be difficult to predict precisely whether the temperature will go up by 1 degree, 2 degrees, or the wind will increase. We'll get less precipitation by 10%, by 9%, I don't know, by 8%. It's very difficult to predict. But the variance, I think, is the key. Can we predict the variance? The variance is, for example, the extreme events. We will need to handle the damages from the extreme events. We will need to guarantee the supplies. So the continuity of the supplies is key from our point of view. We want to provide the electricity, we want to provide fuels, we want to provide water at all times. So extreme events make it difficult for us to do that. So we want to know what kind of extreme events are going to happen, how often they are going to happen, what we need to do in order to adapt to them. And the extreme events are the tails of the distribution. Can we predict the tails? How long will be the hot spells that we are going to get? Will the power stations be able to hold 20 days of 40 degrees, maybe, if we get such an event? Can we survive the winter with less sun, maybe once every 3 years? It may be like that. We get a big storm all of a sudden, instead of the standard 1 week cold event, maybe we will have a 2-week storm, and we rely on PV. We want to be 80% PV. Did we plan our storage in it to handle this? So long cold spells with no sun is very critical. Long periods with no rain, again, we need to keep the reservoirs, we need to have our systems running, we need to plan all of that. Can we handle? Okay, so on average annually I say, okay, it's okay, no problem. We don't know today whether we will need 3,500 million or we will need 3,600, but on a daily basis, can we supply on a daily basis the needs? And here the variance is critical. I want to mention that for the oceans, there are a few effects also. I mentioned the algae, but also, of course, the water temperature, the currents in the water, the wave patterns. We may want to put PV on the sea. Okay, so what effect will the wave changes in wave pattern have on the PV in the future if we want to rely on that? So for the ocean calculations, we also want to have a decent computation center, and I hope that Chial, our research center for the seas and the lakes in Israel, will participate in this computation center and can provide information on the sea and on the lakes in Israel. Thank you.
Thank you, Gideon. And so we understand that we are facing all kinds of adaptation efforts, and each field has its own sensitivities. And as each of the ministries go deeper and deeper to understanding the impact of climate on their field, more and more interesting questions arise. And now I ask Professor Colin Price to come on board and explain the complexity of modeling all those fine details. Please, Colin.
Thanks, Nir. So I think the reason that everyone is here at the COP at the moment is because of the forecasts that we have received from the IPCC over the last 20, 30 years. And those forecasts come from the models that we're talking about. Without the models to tell us what may happen in the future and give us different scenarios, there's nothing really, we wouldn't be talking here today. So the models really are giving us likely futures, not the true future, but something to work with and to adapt and to look into the future. So what are these climate models? So a climate model is basically a set of code, which is maybe millions of lines long. But the problem with the climate model is if we want to predict what's happening on the globe, we need to really simulate the whole planet. We can't simulate what's going to happen in Israel or in Morocco. We need to run everything because basically the atmosphere, the oceans are liquids. They flow from one place to the other, and they don't stop at a certain boundary. So we have to actually divide the planet into these boxes, or like pixels. On your camera, you've got a certain amount of pixels. So we have these grid boxes, which are both horizontal dimension, but also vertical. They have to go up into the sky because we have to develop clouds and we have winds, but they also have to go into the oceans for ocean currents, which are taking water, warm water, the jet stream north and mixing the oceans. And in every grid box here, we have to basically solve all of the equations that explain how nature works, and then transport some of this information between boxes. And we have to do this every, say, 15 minutes in the model and run this for 50, 100 years into the future. So it's a huge job. And the main problem with the IPCC models is that in order to get a result in our lifetime, we have to run these models with some finite resolution. We can't run global models on 1 meter, can't run them even on a kilometer. And most of the climate models are on maybe 1 degree, so it's about 100 kilometers by 100 kilometers. And in this box you can see in the middle, it's basically all the processes which happen within that 100 kilometers of a climate model. And the main thing that happens in those small scales are clouds. and storms. So everything that happens within the grid box, which is too small, smaller than 100 kilometers, has to be what we call parameterized, or assumptions have to be made. We have to figure out how we're going to take the large-scale parameters and estimate what's happening at the small scale. And this is from ice sheets, clouds, vegetation, ocean currents, the interaction at the surface. And this is where the uncertainty comes into the climate models. When we talk about what may happen in the future, it's not because our physics isn't good enough in the model. We know pretty well how the world works. The problem is we can't simulate this at the smallest scales we want. If we want to simulate a cloud or a thunderstorm, we have to start with producing droplets. Droplets occur at microscopic scales and then into millimeters and eventually into big thunderstorms, but we cannot do that on a global scale with climate models. Now we have improved over the years, and you can see from the first assessment report of the IPCC on the top left, the scale of the models were about 500 kilometers by 500 kilometers. The second report, the fourth report, and this shows just the topography over Europe and the Mediterranean. You can see in the first assessment report in 1990, it's very difficult to see where Europe is even. By the time you get to the fourth report, AR4, you can already see the Alps, and you can see the Mediterranean and Scandinavia, and we've improved even more in the fifth and the sixth reports. And on the right, you can see the vertical resolution too. So we have to decide how many layers we want in the atmosphere, how many in the oceans. And again, the more resolution, the more computing power we need. And it turns out the computing demand increases inversely with the cube of the horizontal resolution. So if we double horizontal resolution, we go a factor of 8 up in the amount of computer time we need. And so most climate groups in the IPCC don't go to the very high temporal resolution. But if we want to predict what the impacts are going to be locally in the future, then we have to go through this series of decisions. The first one, we have to talk about scenarios of emissions. In the future, what are the different scenarios, moving to renewables, not renewables, and economic growth, population. Once we have the emissions, we have to then convert that into concentrations in the atmosphere. How much will remain in the atmosphere as CO2, methane, other greenhouse gases, aerosols, particles, and how much gets taken out by the oceans or by the biosphere. Once we have that, these scenarios of the greenhouse gases into the future, we can then put them in the global models to try to estimate on a fairly coarse scale the temperature, rainfall, sea level rise, frequency of storms. The next stage is where we are now. We have to go into regional models, high resolution models which can resolve the mountain ranges, can resolve islands, and that can also give us the extreme weather which may result from the global climate change in the pink box above. And then once we know what's going to happen on a regional fine resolution, we can pass this on to Gidon and Noga to get the impacts of flooding, food supply, sea level rise, effects on our ports, etc., etc. Each of these stages, there's a lot of uncertainty. We're talking about what will happen in the future. So this results in large uncertainties eventually, and we need to run these models many times. It's not good enough to run the model once. We have to have what we call an ensemble of models. We have to run these 50 times with slight changes in the concentrations, in the emissions, to see what's most likely to happen in the future. And we get these kind of spaghetti plots. And if all of them agree, then either all the models are wrong, or we have more confidence in them. But if they're all completely different, then we have very little confidence in what's going on. So I think the biggest impact locally when we're talking about high resolution models is on the rainfall and severe weather. Maybe less so on drought, maybe because that's fairly common over large scales. And we can look here at the hydrometeorological extremes over the last decades. On the right-hand side, the dots show you the number of events globally which caused more than $1 billion in damage, the circles, and the bar shows you the actual dollar damage for that decade. So at the bottom left, we have the 1980s, the 1990s, 2000, 2010s, and you can see that we have a dramatic increase both in the number of events and the dollar damage of these events. And this is where the big impacts are coming on our society and on our economies. If we can show this little movie. So we need to go really from local scales to global scales. And if you look at the simulation, You can see here we're simulating individual clouds. You can see the ground at the bottom. Very high spatial resolution to get these clouds, the rain forming in weather systems. But we have to go from calculating individual droplets and clouds to then zooming out to get the weather system. Now we're looking at it from above. And you can see as a satellite would see these weather systems moving, say, across Europe. And then we have to move even further out and go to the global scale to see how these are going to change as we change those initial conditions of the model, when we change the input of the greenhouse gases, the different scenarios. And we'll see, probably in a few seconds, we'll go then to a larger scale where we're now simulating this over Europe, and we can zoom out to get, again, for the whole globe. And we have to do this on a global scale, really, because there's interaction all over the planet. There are no borders between countries when we go up into the atmosphere. Let's go to the next one. So the future basically is going down to kilometer scale global models. We're now at 100 kilometers. We want to get down to at least 1 kilometer. And this is a simulation, actually, from GFDL in Princeton, NOAA. And this is a model you're seeing here, which is at 1 kilometer resolution around the planet. And basically, once we can simulate at 1 kilometers, we can then start to talk about things like food security, water security, public health, infrastructures, coastal flooding, habitat loss, agricultural yields, renewable energy potential, even national security, regional geopolitics in the region, ecosystem services, biodiversity, disease spread, wildfire risks, air quality, and more. And to end with the air quality, this is a simulation you'll see, which is starting now, shows actually the aerosols at very high resolution. This is a simulation of the future. So here you have different particles. Aerosols are solid particles in the atmosphere, things we can actually see, although they're microscopic. And the different colors are from different sources. But just look over North Africa, which is the dust, the desert dust in our region, although there's also from biomass burning, there's from pollution in the yellow, sulfates from industry. And the date is at the bottom left there. We're now around 2010, but this will keep going until about 2060. And with these high-resolution models, we can also estimate how air pollution is going to change, dust storms, the frequency of dust storms, which are also important for many other things, including generating energy, especially solar energy, when you've got aerosols being deposited on solar panels. And so there definitely is a need, if we want to go down to the regional scale, to see the impacts on local countries and local infrastructures, and in cities, we have to go to this high-resolution simulations. I'll just end by giving credit to these three guys who last year got the Nobel Prize in Physics for developing climate models. And I think it's important to realize that these models are heavily based on physics, the laws of physics. They're telling us what happens when you change the greenhouse gas. And although there's a lot of computer science and mathematics in them, they're based on physics. And so they give us a very good estimate of what is likely to happen in the future if we do A, B, and C. And, but again, these models have until now been on fairly coarse resolution. And the next step is really to go to these high resolution, 1 kilometer resolution in the future, hopefully in our regional center. Thank you.
Thank you, Colin. So you see that for the questions that are really interesting for the adaptation efforts, we must go to simulate those extreme events like Noga and Gideon talked about, and then to get those extreme events, you must zoom in on the weather patterns and get to the high resolution, and you have a lot of physics inside, and this physics need the technical infrastructure in order, of course, the scientific expertise, but also the technical infrastructure, and this is where initiative of establishing regional climate computation center gets in. So, as Colin said, we have for the IPCC reports, etc., there is a working groups arranged by the World Meteorological Organization that groups of scientists all over the world deal with simulation of the entire planet. And when you read those IPCC reports, they are based on those science. But in order to get to the regional level, you must do it in a higher resolution. And to do it in a higher resolution, you cannot do the entire globe. So each regional center takes a part of the globe and focuses on it and does it in high resolution. So this is, again, a world coordinated experiment. It's called CORDEX, and the coordinated regional climate downscaling experiments. And there are domains that are defined for such a thing. This entire effort was established in 1980 and is going on for the last 40 years. Now, here you can see various domains that were defined in the CORDEX framework. And you see on the left the Europe CORDEX region, and the center the Mediterranean CORDEX region, and on the right the Africa CORDEX region. And of course, the expectation is that centers, regional centers with the scientific expertise, with the technical infrastructure will take over and will make those high resolution climate forecasting for the region. Now you start to see maybe that there are some problems in the concept. Why there are problems in the concept? Because, okay, if you look on the Europe region, first of all, if you try to locate where Israel is, you'll find out that it's really, really on the border of this square or rectangle. The same is true for the Mediterranean region. So these are two domains of CORDEX that actually are not really good enough for the region of Israel and the Eastern Mediterranean. The other thing is to think who will run those simulations. So of course, when you think about the Europe CORDEX, you think about Germany, England, France, Italy, Sweden, etc., etc. So we have a lot of high-tech countries that are able to run and produce, and indeed, this is a very rich CORDEX region with a lot of simulation of different models of different resolution. Typical resolution of simulation in this region is about 11 kilometer as a baseline, and most centers do it at higher resolution. But they, of course, tune the model to their region. So think about Germany running a model for Europe region. It will focus, of course, on the interesting thing for the region of Germany. It may be the ice storms or the rain events in the summer or other events of the European heat waves. It will not necessarily be those phenomena that are critical for the Eastern Mediterranean. For instance, it might not be very critical for Germany to simulate properly those dust or aerosol particles that Colin has just talked about, which are very important for PV production in our region, etc. And now if you look on the Africa domain, now try to think what are those regional centers that are capable of running high-resolution model in this region. And you'll find out that actually most of the models run in this CORDEX region are not done by a regional center in Africa, but rather by some of the centers in Europe that also run auxiliary runs for the sake of Africa. Now, of course, they don't run those auxiliary runs at the same resolution and fine-tuning as they do for Europe. And therefore, if you are in this region, you are in a problem. And to show you the example we took for Israel, in order to supply the different ministries with the information needed for the adaptation efforts. As you saw, we have a governmental decision that says all ministries must prepare the adaptation plans until the end of 2023. All the ministries are working. Each of them want information. So we took the Codex runs of Africa, in which we are not on the border. We are situated relatively far from the border of the region. And we looked what it means to Israel. So the coarse resolution of those models is about 45 kilometers. You see that Israel is very thin in the shoulders, okay? It takes about 2-3 pixels and you are out of Israel. So you don't see this complexity that Noga started her lecture with. You remember she told about the different climate region, the different topographies you have in Israel. We go from Jerusalem at a height of plus 900 meters to the Dead Sea minus 400 meters over a distance of about 15 kilometers. Okay? This complexity is complexity that influence the climate and weather very significantly. Each of us Israelis know that well. In the Dead Sea, it's hot, it's dry. In Jerusalem, it is much more cold. It's colder and it's much more precipitation. Actually, the amount of precipitation in Jerusalem is about the same like in London. Okay, it's not spread the same, but it's the annual amount is very similar. So you cannot do it in such a model. And we took a list. You see here the list of models in the Codex Africa. We have here runs by the Danish Meteorological Service, by the Netherlands, by Sweden, by German centers, etc. These are the centers that run the Codex. And then we try to compare it with observations to see if we can use it. And then you find out that you cannot fit it well because it cannot resolve the details of our geography and our climate. You can see here the map of Israel, and to understand the meaning of this resolution, look on the left, you see a map with the coarse resolution of this 50 kilometers like we have in the Codex Africa models. And as you go more and more to the right, you see higher and higher resolution. On the right, you see already 8 kilometer resolution, and you start seeing the Israeli topography. You start seeing the Dead Sea, you start seeing the Sea of Galilee, you start seeing the Judea and Samaria hills, and you start see the coastline in the appropriate orientation. These are all important ingredients of the weather patterns in Israel. Without them, you cannot. But you don't have such models. Okay? The Codex Africa runs at 50 kilometer resolution. And actually, the only available Codex runs up to now are based on CMIP 5, which is the previous set of climate runs, and not on the recent IPCC CMIP 6 set of models. And this is what happens when you compare it to observations. You see this bell curve, which displays the distribution of temperature, okay, like a Gauss shape. And this bell shape, actually the dark line is the observation. So today, if we took, this is summertime in Jerusalem. Summertime in Jerusalem, the average temperature is about, at noontime, is about 30 degrees, okay? Almost like here outside. If you look on the climate models, you see on those colored lines, and you see all of them are off significantly. they give an average temperature about 37 degrees in the current climate. Okay? If you look on the tail that Gideon talked about, what happens to the tail of distribution, because on the tail of the distribution you have the extreme events. You see that according to those rough models, already we should experience in Jerusalem temperatures of above 45 degrees, 50 degrees. Now, for 150 years we were measuring temperature in Jerusalem, and we didn't reach the 45 degrees. Okay? And according to those models, it should have happened quite often. So you start with a model such as that, and now you are supposed to give a prediction. When you already started with a shift of 6-7 degrees relative to observation, and that your tail is totally off. This, of course, makes the prediction of what will happen if we will change by 1 degree, 2 degrees, 3 degrees, a little bit a ridiculous discussion. Because if you start with a model that is so off, how can you really give something? And you know, I'm standing in front of those ministries that want the prediction as the head of the meteorological service. And I want to give them good data. I want to give them something solid which can support the decision making. And when I give them the forecast, I'm, you know, putting such a disclaimer on the report because of this issue. Now, so coarse grid is not enough for temperature, for heat wave. Coarse grid is not good enough for floods. We have a very small river basins, and we have cities. And when you look on cities, these are pictures, you know, not from the third world or something like that. This is the center of the coastal plain of Israel. On the left, I think it's Tel Aviv, high-tech city, etc. And this is what happens when you have a very extreme rain event in Tel Aviv. So you want to give, of course, the designers the proper statistics to understand what kind of rain intensities will occur in the future. Okay? What kind of preparation, how to build the infrastructure, because those urbanized centers become denser and denser, more population and more roads and more bridges and more buildings. How to build those cities properly, how to make sure that such sites will not become more and more common. And this is what science tells us. You can see here on the left, on the map, a rain event in Israel in 2016, which caused flooding on the north of Israel, in the region of the Kishon. In the center, you see a very good global simulation, which is at the time the simulation of the European Center for Medium-Range Weather Forecasting, the high-tech of global forecasting. This is a 16-kilometer resolution model. And on the right, you can see a run, a regional run by us with a resolution of 2.5 kilometers. Now, the different colors give you the intensity of rain. You see that the event, why we got the flooding? We got the flooding because the red color, okay? It's like a traffic light where the color gets more to the red. It means the intensity of the rain is stronger. We are here talking about 90 millimeters that fell within few hours, okay? And flooded the river. As you can see from the very good central picture of a global model, it didn't reach the red thing. It didn't reach the red color. It didn't give the rain at the proper location, okay? Only when you get to the high resolution, you suddenly see those red stripes. You see those strong rain intensities. And this is because as Colin said, when you model clouds, when you model rain, you must go down to the size of the phenomena you would like to simulate. So if you talk about rain clouds, this means getting to a scale of about a few kilometers. Only within this fine you can simulate the convective clouds which cause those floods. And as I said, towards the sixth assessment report, we have a new set of climate modeling, global climate modeling. Now is the time to take those global models, CMIP6, and downscale them. Downscaling, that is to take the regional models and do it in high resolution. So, what is our aim here? To take the region and start doing climate simulation at higher and higher resolution as we zoom in on our region. The first region we are going to cover is the blue region, which, as you see, covers the entire Mediterranean, a significant part of Europe, and the Middle East, including North Africa. And this will be a kind of a Cordex run, but Cordex Europe or Mediterranean is a smaller one. We don't want to be close to the boundaries, and therefore we extended it a little bit. So it will go to the east into the Persian Gulf, to the west into the Atlantic, and to the south deep into North Africa, so we can get all the spectrum of phenomena we know that are important for the Eastern Mediterranean. So we are going to do those runs, and then on the red region, this is the Eastern Mediterranean, we are going to do a higher resolution run of 2.5 kilometers, like the one we showed in the previous slide. This will allow getting really the resolution of the clouds, of this significant weather phenomenon. Now, if you see on the bottom what kind of computing power you need for those runs. As Colin said previously, as you go to higher resolution in space, you need first of all to have a higher resolution in the vertical, and you need also to have high resolution in time. So the factor is very significant. And actually, if you want to run this big blue region, okay, for 50 years in the past and 100 years in the future, it takes 700 computer cores running for half a year. So it's a computer run that runs for half a year on 700 computer processors, and this allows you to do this computation. If you want to run the smaller region, but in a higher resolution, actually it takes you more. You need about 2,000 computer cores, and for the same time, for half a year. So to do the entire project, one run, it will take about 3,000 computer cores for half a year. And this entire effort will result in one scenario, one model. So actually, if you really want, as was said previously, an ensemble of various scenarios, of various models, of various parameterization of physical properties, you must do it not once, again and again with different scenarios, different variation of physics, etc. And therefore, you need a lot of computer power, and it will take some time. The typical way, if you go to those climate computation centers around the world, in the OECD countries, etc., they do it by high performance computer, what is called supercomputer or HPCs, and you see things like that. For instance, the image you show, the animation of aerosols that Colin showed previously, was done in DKRZ, and these are the Deutsche Climate Research Center, and this is the way such a climate computing center looks like, a big center with dedicated computers which have those processors that are connected to each other, very high performance computer cores that are connected in a very high speed between themselves to allow them to have those transactions of data between them during the computation. And you can see on the top an example of a big center like the DKRZ Center in Germany. On the bottom, you can see the Cyprus Institute example. It's much smaller, but still the same type of solution. But recently, there is a new option. And the new option that now technology is available is to run such models in the cloud environment, in the commercial cloud environment. What you see here, for instance, this is a project of World Bank with the Cosmo Consortium for the region of Central Asia to see how you can run a methodological model in a cloud. And they took a region of about 2,000 kilometers and did a resolution with a scale of few kilometers to see how they can use the cloud infrastructure, the commercial cloud. And indeed, it turns out that, and they did it on the Amazon cloud, on the Google cloud, and the Microsoft cloud, Azure, and actually they got quite similar results. They succeeded to do it in a time which was more or less comparable to an HPC. Why? Because those runs, or those commercial cloud servers have very strong CPUs inside. Okay, so they can really do fast computation. And if you run it on one of those racks in the computing center, you can do such a run under $30 per run. Okay? This is the cost for run, not a climate run, but a weather run for 3 days at a resolution of a few kilometers. It's already this number, and this is competitive, quite competitive with the regular HPCs. So our concept is to use cloud infrastructure to run the climate model, and the idea is to use. Israel recently had a cloud services tender called Nimbus, and both Google and Amazon won this tender, and they are building dedicated data centers in Israel for cloud services to the government. And we are going to use those platforms in order to run those climate models. So what is on the plan? So the start of the center operations will happen next year, 2023. This will be a shared resource for the meteorological service, the hydrological service, the ocean research center, and for the academia. That is, all those research institutes that run models will use this facility. It will be about 10,000 computer cores that will be available. And all those modeling will result in high resolution, high definition climate modeling of rain intensities, of winds, of extreme events, etc., of the hydrological modeling will give river discharges, the ocean modeling will give waves, etc. And this will all go into a database of high resolution forecast, regional forecast. As you saw, those regions, it will comprise big parts of our region. And all of them will be open to the public in Israel, open to the private companies, and open, of course, to our partners in the region, which will be able to use them. And therefore, we wish to get within a few years to putting for decision makers, not only in Israel, for companies not only in Israel, this detailed forecast, high resolution data to be a good basis, a solid basis for the decision making. And now I would like to invite to the floor Dr. Kleanthis Nikolais, who is our partner in Cyprus. And actually, as I showed you before, the Cyprus Institute already has an HPC, and we are already working with them in building those climate models.
Thank you, Neil. Thank you. Well, hello, good afternoon. Thank you very much. Thanks very much to the organizers for this meeting, which is very useful, and it's going to be for the mutual benefit of our communities. So a few words about the Department of Meteorology. Is the governmental authority of Cyprus for the study of the weather and climate. We are not a research organization, though we keep a lot of data, and we have been heard a lot of things about data and about modeling, and the data are very essential for modeling because with data we train the models. Our mission is to collect those data and to provide all the information related to weather and climate for all the economic and social activity of the island of Cyprus, and achieve high quality of services for the benefit and the general welfare of the public and the protection of the property of its citizens. But, of course, climate change, which is the issue of this COP, is a risk causing a factor of uncertainty over our area. So the general welfare is in danger. The general welfare of our communities is in danger. Some essential dates. The first weather station over Cyprus was established in 1887 when Great Britain bought from the Ottoman Empire Cyprus. It was a deal of money. So it was bought, and the first weather station was installed at Larnaca, and it's operating until now. In 1963, Cyprus signed the MOU, the WMO Convention, as a full member, and at that day near, IMS was funded by WMO. The numbers of the resolutions are successive for the building of your premises in Tel Aviv. Our efforts for developing were limited by the Turkish invasion of 1974. In 1976, we established the weather forecast unit at Larnaca Airport. And since 2000, the Department of Meteorology of Cyprus is using the technology, the IT technology, and so on and so forth, automated observations. We have installed more than 45 automatic weather stations over the area of Cyprus, more than enough for the area of Cyprus. And I'm showing data as recorded, then people were writing, not punching. So data from that very first weather station at Larnaca. And of course, I will repeat that the data and the flow of data between collaborators is very essential because we train the models. Neil said earlier that if we start at 2000, let's say in 2022, and go further till the end of this century, we need data. So Cyprus has the essential data to train the models for the area. Weather and climate. Weather and climate are environmental conditions, can affect the economic activities and the social life in our place. The area of the East Mediterranean is identified by WMO as a climate change hotspot. The word was used twice today. So climate change is present in the area. It is not something to come. It's present, and its evolution, if examined, if historical data are examined, are going to prove that we have rising temperatures of 1.5 degrees if compared to the era of 1961-1990, which is the base conditions for climate change. Climate projections over the area are not that optimistic, since scenario business as usual continues. Then the forecast for our future climate is pessimistic, possibly of an increase of more than 5 to 6 degrees C by the 2070 is possible over our area. My next 3 slides are going to be about the initiative of the President of the Republic of Cyprus, this initiative for EMME region, East Mediterranean and Middle East, which is based on the fact that climate change is present in EMME region, and we can recognize the danger caused due to climate changes, while climate projections, if business as usual, show a clear increase in the temperature, decline of accumulated precipitation, and an increase of the frequency of hazardous weather. This initiative of EMME region, the area of East Mediterranean and Middle East, consists of 18 countries, between them, of course, Cyprus, Egypt, Greece, Israel, Jordan, Kuwait, and so on and so forth. It's a house of almost 500 million people, this EMME region. This EMME region is in danger due to the climate crisis, and this initiative of the President of the Republic of Cyprus aims in bringing in the countries of EMME together to coordinate a concerted regional response to address the climate crisis in line with the goals of Paris Agreement. These almost billion people and the 18 countries comprising the EMME region are at the risk of 5 degrees increase of the mean annual temperature if we do nothing. So something has to be done. We have to do something. The MSCCI, the EMME Climate Change Initiative, is inaugurated here in Sharm el-Sheikh by their Excellencies, the President of Egypt and the President of the Republic of Cyprus. The EMME Regional Action Plan is to set of proposed projects and services that were put together based on the work of 13 thematic tasks comprising of about 240 scientists. The Cyprus Institute, a leading academic organization over the area of East Mediterranean, is coordinating the academic research part of EMME, and the aim of this is to identify the future climate scenarios and preset actions on each scenario. But everything has to be under an umbrella. Cooperation is the word. The need is identified. The previous speakers said about the need. We have to go down into shorter distances. We have to increase the levels of our interest and decrease the level of uncertainty. Only cooperation. Since the need is being discussed, the cooperation is what is going to give a solution to the problem. Weather and climate are unifying environmental parameters. It's something which is flowing. My weather is going to affect Israel weather. So the good knowledge of the weather over Cyprus is the good knowledge over the weather for the weather over Israel. It is true that weather forecast has great needs on HPCs, on high performance computing. This is true. We can go back when we started forecasting. We could forecast for 1 or 2 days, and the time needed in a resolution of 100 kilometers was almost half a day. Now we feed the system with data, and in a high resolution local model, we have after 3 hours a forecast for 3 to 5 days. But climate is not the same as the weather. Climate, as shown before, needs to dig in, to go downscale, to get more information and support all the cells with the needed information. So the today need for HPC power of climate modeling with resolution 2050 kilometers, if this is enormous, then imagine the enormous power which is needed to downscale, to go down to 2 kilometers, which is a must also for the climate forecast. The weather phenomena like dry spells, intense precipitation, dust events. You know that dust events have been climbing to the number of 130 days per year the recent years over the area of Cyprus, over the area of Israel, of course. When I was a child, in the middle of past century, we had only 2 severe dust events over Cyprus, lasting only for 2 to 3 days. I don't want to remind you the more extreme weather event we had in our area of September 2015, which caused not only a destruction in social life, but also fatalities between the community. So the need of cooperation is high, and the need for high resolution climate modeling is even higher. The Department of Meteorology of Cyprus is a strong fellow with a very strong commitment in regional and international cooperation. The Department of Meteorology of Cyprus and IMS have a bilateral agreement, a bilateral cooperation resulting in our mutual benefit, which is, we've said it, we have done it. That's it. The Department of Meteorology of Cyprus, IMS, and HNMS Greece have since a year now a trilateral cooperation, beneficiary for them. The MCCI serves in the spirit of cooperation. Merging our forces for a concerted response is a primarily need for the detailed regional climate forecast. The Cyprus Institute is going to assist, since it's going to run its own climate model in high resolution. The initiative of the IMS is alongside with the Cyprus Institute TRI. And of course, I trust in the name of cooperation that the spirit of cooperation between IMS, Department of Meteorology, and Cyprus Institute will be a success story for the future and for the benefit of our population. Thank you very much.
Thank you, Kleanthis. And now I call the panel members to the stage and allow the audience that was very quiet up to now to ask questions if they have. Okay, so the floor is yours, please. You are devastated. Okay.
So, thank you all very much. So the Mediterranean is a hotspot, as we got it from all of you, but it's not only climate change problem hotspot, it's also government and politics hotspot in many ways. And side of Israel and Cyprus, how can we narrow this gap and collaborate with our data with our neighbors?
The other one.
So we are dealing about the meteorology hotspot of the Mediterranean. Of course, there's a political problem in Cyprus. I have said many times in conferences, international conferences, and in WMO also, and EU MedNet, the European Meteorological Network of HNMSs, that weather is unifying, climate is unifying, so it mustn't, the politics mustn't be an obstacle to the flow of information.
On the contrary, it can be an opportunity, and you, Cyprus, can lead this as the middle country, the middle person in negotiating and bringing the data.
As I've shown, the initiative of the President of the Republic of Cyprus about EMME region takes into account also our, let's say, political refusers. Thank you.
If I can continue what Cleanthus just said, indeed, this is unifying. So we signed those bilateral and trilateral agreements in the last years, exactly because all countries understand the importance of tackling those together. The Department of Meteorology in Cyprus is small. The Israeli Meteorological Service is small, and we can work together. Okay, so when we think about the scientific communities, okay, this is quite natural. We are in the same region. We are tackling the same challenges. So it's very natural. And Colin can tell you about the cooperation exists. By the way, I will pass the microphone. By the way, those researchers, joint researchers with Cyprus are much before our trilateral or bilateral agreements. This is one thing. The other thing is that it's not only with Cyprus and Greece. We have collaboration on the entire southeastern Europe. We have a project that's called CMUS, Southeast Europe Multi-Hazard Early Warning Advisory System. We are now building a collaboration with Palestinians and Jordanians, and hopefully we'll extend it even to Egypt. So indeed, the climate change challenge that is joined by all of us is really a place where a lot of cooperation can take place, and I pass the microphone to Noga.
I just want to say that risk and instability are also an opportunity for collaboration, because if we face the same issues, the same problems and threats, and we can unite in order to solve them, it could be an opportunity for collaboration. And Israel, at least, has a clear interest in solving the neighbors' climate risks, because we don't want to have countries with large numbers of climate refugees. So I think that there's a mutual interest that could result in collaboration instead of conflict.
I just say that Cyprus has a role to play as the moderator in the area, the kind of neutral, the adult in the room maybe. Because if Israel can't lead this regional cooperation, it's very sensitive. And so we've already started working with Tel Aviv University, with Cyprus Institute, on impacts of climate change on the financial sector. And Cyprus has brought to the table people from Egypt, from the Bank of Egypt, and from Italy, and they also have connections in Lebanon, which we don't have connection. So I think Cyprus is actually, it's kind of the anchor, the hub for solving some of these regional problems in the future. So very happy to have our partners here today.
I would only wanted to underline what Nir said about Jordania and Lebanon, which under the United Nations Committee, a specialized organization, brought Israel, Jordania, and Palestinians at the same table for this very severe issue. The weather is unifying. That's it.
Hello, thank you for your discussion about the regional climate disasters. Nowadays, climate challenges are global, but we are faced so many problems in the Middle East. For example, as you mentioned about the dust, drought or flood. I want to ask a scientific question. This is a computation process. We have a big data. What is the outcome? For example, when we can achieve a solution for the dust problem in the Middle East. Is it possible to mine data to achieve a solution or no?
So I'll allow the colleagues to expand on my question, but this is exactly the idea. The idea is to build a common database, solid database of scientific facts, and then allow all sectors, all partners, all countries of the region, companies, etc., to use this data in the more or less sophisticated ways, and to get out of it the decisions. Indeed, there is, after you set up the scientific basis, you're not finished. If you remember the slide of Colin, who said, okay, you have those global models, you have the emission scenarios, and then you have those global models and local models, but then you must also have this layer of decision support, how to translate it to action, to appropriate action. And this is something actually in the focus of the two chief scientists beside me, so I hand the microphone to them.
I'm not sure if I understood correctly. You mean, can we do something about to mitigate or to adapt? What did you mean?
First, mitigate.
Yeah, mitigate. So mitigate is the next step. I think we are not there yet. On how to affect the weather, it's not easy, but it's I think it's a good approach to think about. Maybe we, if we understand the models well enough, then we know what parameters are important. Perhaps in the future we'll be able to understand how to mitigate certain effects, certain events.
I'll just add that for adaptation measures, we need high resolution spatial information, and then we can tailor high resolution efficient adaptive measures. So without having such information, you can try to promote adaptation measures, but they won't be efficient, because they won't be directed to the specific risks and sensitivities of the specific location. So we really need this information to move forward.
I'll just say something about the extreme weather, and now there's a school of thought in our area that you can use machine learning to try to give forecasts of extreme rainfall, droughts, fires, based on historical weather patterns. And we've got lots of data, and now with machine learning, artificial intelligence, some people think that firstly it can be done fairly quickly, and the question is whether it can be done better or not than the physical models that we use today, which are based on equations, the laws of physics. But for climate, we don't have learning data to teach us what may happen in the future. But for weather, it's possible that using lots and lots of data, we may be able to improve the forecasts for the next few days using machine learning.
We focused here on the physical models. On top of those physical models, you need more models. For instance, you want to understand, okay, there will be changes in the patterns of temperature, there will be changes in patterns of rain, of evaporation. What will happen to the crops? What will happen to the yield? Okay? One question that is very interesting for the agricultural sector. The energy sector wants to know what will happen to the demand, to the electricity demand, especially what will happen to the peak demand. What will happen to the PV production in situation where you need the high demand? How to get organized? So you need, on top of the weather modeling, you need the modeling of the socio-economic effects of the weather. So actually, in this time where many bodies are mapping risk, as you get and map the risk in a more scientific or engineering way, so that you have a curve, some function that connects you between the temperature and or other elements, and for instance, an element you would like to understand, such as the probability of forest fire, of big forest fire, etc. As you do it more accurately, as you build those functions or those relations in a more accurate way, then you will be able to use the detailed climate information for good prediction of what will happen to the forest fires, for the electricity consumption, etc. So actually, and those models can be based on artificial intelligence. They can be built on other things. But there's a call, and actually, in tomorrow in discussion that Noga will lead, we'll talk about the kind of information layers and mechanisms needed to give good practical decision maker tools.
Thank you very much for your presentation, really interesting. I just wanted to ask, because you made mention of the data from Africa and how it's not being produced by Africa themselves, but instead is maybe some companies from Europe or other parts of the world. And I was just thinking how we can be able to help Africans produce their data so that it's much more accurate in a way that is not only benefiting African, but is benefiting entire world, because we all live on one earth. No matter where you live, we're going to be affected by climate change. And if you see across, especially Sub-Saharan Africa, where I come from, there's huge potential. Young people, the forest resources that they have, and in terms of data, we don't have, because the data are really scattered all around the place. And so I don't know how we can be able to harness some of the potential in Africa, especially Sub-Saharan Africa. Thank you.
So it's a good question, and I think that is a question that WMO, for instance, tackles, tries to find a solution. As I showed, the existing mechanism is through the Codex process. There is a Codex Africa, and you have those European countries running the models as part of their global efforts. They are not only running on Europe region, but also on Africa region. And I think that in order to do it, Africa is big, a little bit bigger than Israel. So in order to do it in high resolution over Africa, first of all, it might not be needed in the entire continent. So there are those places where you have sharp gradients, mountains, valleys, etc. You have places that are near coast, but maybe there are regions of deserts, etc., that are uniform, and you can and the rough model will be good enough. So it might be that you can map those regions of Africa that need the high resolution. And now the question is to find the budgeting, and there are the the international donors, the World Bank and other entities that might be able to support such an endeavor. I think this is on the table in WMO discussions. We will have a Congress of WMO in coming May, and I think this will be one of the issues that will be raised. So thank you very much. For me it was interesting. I hope for you as well, and thank you all my partners here.